me? Do I need a microphone? I think I'm okay, am I?
You're actually listening.
Great. So yeah, I head up the very catchy title of Department of Aging, Rheumatology and Regenerative Medicine. That's basically an eclectic bunch of people who couldn't be managed by somebody else. So to put them under my auspices, under the strong and stable leadership, to take a word from Theresa May, apologies for that. But actually, yes, rheumatology is an immune-driven disease. Regenerative medicine, actually also. But aging is what we're really building up within this new department of the Division of Medicine. We're set up a new centre to build greater links between the university and the hospital. And I hope recruiting a brand new group of very exciting young scientists to the 4th floor of Richard's old alma mater, the glamorous Rayne Building on University Street in Q1 next year. So we really are investing heavily in inflammation and aging. But my research group is interested in how inflammation switches off. It's a natural, spontaneous process that is actively controlled. And you all know this phase of inflammation very well. If you get heat, redness, swelling and pain because of a bee sting, all of that is driven by, I'm afraid to touch anything, so I'm not going to do anything, by the cytokines and chemokines on the left-hand side that cause heat, redness, swelling. They bring white blood cells into tissue, they eat up bacteria, they kill them, but importantly, these neutrophils need to die by apoptosis. Need to die by apoptosis, and that's very important because that makes them more recognizable to tissue-resident macrophages who eat them up. And the eaten up process of apoptotic cells by macrophages reprograms these macrophages to acquire an anti-inflammatory resolution phenotype, releasing things like IL-10, TGF-beta to help switch inflammation off. And that's the resolution or the going away of the heat, redness, swelling and pain part of acute inflammation. And this phase of resolution has garnered interest and imagination of people over the years because perhaps we can develop drugs based on the mechanisms of action of resolution to drive chronic diseases into a resolution trajectory. I'm going to tell you that's not going to be as easy as you might think, but perhaps propose a reason why that might be the case. So getting back to an old story published which sets the scene for what I really want to tell you about, and that is, does defective resolution drive chronic inflammatory diseases? And instinctively you would have thought that if we can't switch off our responses adequately, then that might underpin the etiology of some chronic inflammatory diseases. And perversely, we have a lot of experience of doing human experimental medicines. And I use the word perversely because we can get ethical approval to do things in humans in about 8 weeks at UCL. On humans, it takes about 10 months to do on mice via the Home Office. So we are incredibly nimble in our ability to do stuff on humans, primarily introducing irritants or antigens into the skin of humans, young, old, and even those with chronic diseases. So we use human skin as a window into human immunity. We began to get interested into immune senescence because it's a really great model. You know, these are old people, and I'm not saying age is a disease, but age brings with it defects in our immune system. Our innate and adaptive immune system is impaired. Vaccine efficacy reduces from about 80-90% when we're young, when we're old, down to about 89% efficacy when we're young to about 30-40% when we age. And this is all down to T cells, perhaps dendritic cells as well. Defects in wound healing as we age cost the NHS £7 billion per year. And this becomes important because the amount of people aged 65 and above is going to increase about 3.1 billion by 2100. So not only is the problem of immune aging an issue, but there's going to be lots more of us with it. So we asked from our area of resolution biology, could some of these defects in immune aging be explained, at least in part, because of defective resolution biology? And one of the models we chose from about 9 that we have ethical approval for is applying cantharidin to the skin of the forearm of willing volunteers. And this causes a blister. You can see how we apply it here. Top left corner, get a little piece of blotting paper, drop the cantharidin on it, put a little pad on top, seal it over, and if we let it evolve for 24 hours, we can then take it up to 72 hours, we can capture acute onset of inflammation, all of that neutrophilia that comes into tissues, and the chemokines and the cytokines. But if we let it continue up to 72 hours on the other arm, we can capture the resolution biology phase. You with me? You got the model? And we recruited groups of individuals, about 21 young people under the age of 30, and for this study about 17 over the age of 75. And we did stuff on them. We looked at this is how the blister looks after 24 hours, top left panel, in young people, and it's slightly more formed at 72 hours as time goes on. Now the first observation is that in old people, the amount of edema that accumulated, bottom left panel, was significantly less to that compared to young people. But by 72 hours, the process caught up. Then the other thing was, so this was a PhD studentship of a PhD student of mine. And when he took out the fluid from the blisters, young and old people, onset and resolution, and began to look at all of the immune cells that might alter in young and old people over time, and the chemokines and the cytokines and the proteins and the lipids, we saw very, very little difference. Now, it is very unusual for us to have put acute inflammation in groups of young and old people, and at least in the salient features of inflammation, so absolutely nothing. So that's 2 years of a PhD that didn't look promising. But for those of you doing PhDs or postdocs, listen to the words of Jeffrey Bernstock, physiology professor at UCL. If you design an experiment well enough, and your hypothesis is okay, even if it fails, there is something in there that you can redeem and do something with. And that is always proven true for me. When my student went away, yes, he says there's no difference in total leukocyte numbers, young and old, at onset and resolution between young and old people. Cytokines and chemokines, edema was transiently affected, cardinal signs nothing. But what he did find was something quirky in the neutrophils. You all know neutrophils, the most abundant white blood cell in our body, kills bacteria. And in young people, the black on the left-hand side, numbers of these cells declined uniformly over time. And this is what we would expect would occur when inflammation is resolving beautifully. The neutrophils are dying and are being cleared. But when we looked in the old people, on the right-hand side in red, that trend was lost. So there was something amiss, perhaps, with the resolution within the tissue biology of old people compared to young. And so if neutrophils aren't behaving, aren't going away, there's a number of reasons for that. A priori, you might argue, well, perhaps older people, they have more neutrophils that migrate into the tissue. They just accumulate more. 2, they live longer, and there's a literature on that, the neutrophils of old people. Or 3, they're not cleared adequately enough. So we spent a very long period of time excluding the fact that neutrophils in old people do not migrate at any different rate to that compared to young people. They migrate at the same rate. We also discovered that the neutrophils die at the same rate in old people compared to young. And so that excluded potentials of trafficking and death at the site of inflammation. But the one thing we weren't sure about was clearance, and it was when the neutrophils get into the tissue, is their clearance impaired. So how are neutrophils cleared in a bit more detail? Here's a live neutrophil. Neutrophils live anywhere from 6 hours to 18 hours. In fact, at sites of inflammation, you can keep them alive for 36 hours. We now know there's 2 populations of neutrophils, young and old in blood, doing different things. But if we just keep this side, left-hand side, live neutrophils, 2 things just to remember. 1, they have these things called phosphatidylserine, which sit looking into the cytosol of the cell. But it has CD47 and what's called don't eat me signals sticking out of the cell. And this stops macrophages from eating them up. But when a neutrophil has eaten up bugs, when it's done its thing, then these phosphatidylserine, for example, eat me signals flip onto the surface of the macrophage, and the don't eat me signals, CD47, flip into the cytosol. And these phosphatidylserines are incredibly important because when the macrophage sees them, it's got a lot of things on its surface that can engage with the apoptotic neutrophil, one of which is TIM4, top left corner of the macrophage. It loves to bind to phosphatidylserine, and it grabs the neutrophil in place and holds it ready to be engulfed into itself. And when it does that, not alone is it clearing dead neutrophils, which is really, really important because you don't want neutrophils hanging around. They can release bad things that can damage tissue, and they can release neoantigens that can drive autoimmunity, as in the case of lupus. The origin, many people believe, the etiology of lupus disease is the inability to clear debris, specifically immune debris neutrophils. And then when the macrophage eats up an apoptotic cell, it releases good things, like I said in my second slide, TGF-beta, IL-10, to help switch inflammation off. And these are called Reiter cells. The old pathologists in the room, which you just interviewed, will know that a Reiter cell is classically a macrophage with a dead apoptotic neutrophil in it. And that's the process that is involved in clearing neutrophils. And so we ask the question, is any part or many parts of this process affected by age, accounting for the accumulation of neutrophils or failed clearance of neutrophils in the blisters of old people? You with me? And indeed, what we noticed was when we counted the number of apoptotic cells, neutrophils with phosphatidylserine expressed on its surface in the blisters of old people, they were significantly more, telling us that there is indeed impaired clearance of apoptotic neutrophils. So the question is, does the defect lie at the foot of the neutrophil, unable to make itself recognizable to macrophages, and or is the defect lie with the macrophage? So after much ado, we had figured out that the neutrophil, as I said, dies at the same rate between young and old people. It expresses its eat me signals at the same rate as young and old people. It downregulates its don't eat me signals at the same rate as young people. So there's nothing wrong with the neutrophils. They behaved in the usual fashion, young and old people. So the problem perhaps lies with the macrophage. And indeed, through an awful lot of iterative experiments, we had discovered that there was one defect present on the circulating blood of human monocytes and tissue macrophages, not rodents, we can discuss that, was a downregulation in TIM4. The molecule, it is a non-signaling molecule that just simply grabs onto the apoptotic neutrophil via the scruff of its phosphatidylserine neck, brings it towards the macrophage to be eaten up. And there you go, there's levels of TIM4 just to show you downregulated on the surface of mononucleophagocytes of old people in red on the right hand side compared to young on the left, and no other marker involved in nephrocytosis. That lot on the right were affected in any way. And again, long story short, what is regulating TIM4 expression on the surface of old macrophages from old people? Well, P300 acetylates it, drives up its expression, and through a whole lot of other experiments we figured out that phospho P38 MAP kinase degrades P300. And if you do that, then what happens is TIM4 levels go down. What we discovered is that P38 MAP kinase, lo and behold, is elevated in the macrophages of old people. And this is something we've seen time and time again. As we get older, P38 MAP kinase tonically increases in the mononucleophagocytes as we age. And luckily, lo and behold, GSK have a drug called losmapimod that blocks P38 MAP kinase. So we set up a study, again being nimble as we are in academia, 6 weeks for ethical approval, unlike the Home Office for 10 months for mouse work. We could get losmapimod, we dosed it twice a day for 3 or 4 days, put our blisters back onto our old people, and these are old people in red. We could recover TIM4 molecule expression for the time and duration that the drug is on board. And on the right hand side, these again, old people in the black circles, this is the amount of apoptotic dead cells higher in the red old people and reduced back down to that levels of young people with losmapimod on board. Lots of other biology in our papers to underpin this, but what it tells us that in young people there's a modest amount of P38 MAP kinase present in our cells, keeping TIM4 levels under control. As we age, however, P38 levels go up, TIM4 levels drop, and we get this build-up of immune debris, macrophage reprogramming, explaining many of the things we see in the immune aging capacity of old people. So this is what we've seen. Age drives defective efferocytosis and TIM4 expression. TIM4 is controlled by P38, P300, and that if you transiently inhibit P38 MAP kinase in old people, you can make your immune system, at least in the context of resolution, look very similar to that of young people. And we published that in a series of papers over the years. But here we began to think about this a little bit from a drug development perspective. I told you that an impairment of the ability to phagocyte or eat up efferocytosed apoptotic cells is one of the cornerstones for the etiology of lupus. That's an inherent defect that is there. Chronic granulomatous disease is another inherent defect, the inability of neutrophils to kill bugs. Bugs hang around, inflammation progresses. But what about looking at it from the opposite perspective? Is one of the reasons why chronic diseases and aging progresses is because the chronically inflamed tissue has impaired or switched off our internal resolution pathways. And because I got bored and I decided that being head of a department of reckless vagabond academics wasn't enough for my sins, running my own research group, raising kids, blah, 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 I decided I need to do something in addition to that and learn some new tricks. So recently set up a company called Penta Therapeutics. And we think we are looking at understanding the etiology of chronic diseases slightly differently. We wish to resolve inflammation, we want to reset immunity, we want to restore homeostasis. And 60% of the maladies and deaths worldwide are due to chronic inflammatory diseases. And this is the thing. Current treatments block pro-inflammatory pathways, the heat, redness, swelling and pain. The things that drive that are blocked by majority of our current anti-inflammatory drugs. To dampen the clinical symptoms. None are curative, they are ineffective in some patients and have side effects. That is a fact. And it's pitiful when I sit and listen to a rheumatologist give a review on the evolution of drugs in rheumatology over the past 20 years, and it's dexamethasone with a disease-modifying drug with an anti-IL-1, and just combinations of very little advancement. So there's something to be done. And of course, the financial rewards, if you get it right, are huge. The cost of treating chronic diseases is massive. So are pro-resolution pathways actively silenced in chronic inflammation? And if they are, then attempts by some people to actively engage resolution pathways will be futile because they will not be expressed. What you might want to do is wake them up. Are you with me? And then engage with them to see if we can drive inflammation into resolution. That's what we are about, and this is a little snippet of some data that we've done. I was beaten up on mice a few minutes ago. Here he is presenting data on mice. But we had gone back to our old data set. We had two contrasting models of inflammation in a mouse model of peritonitis. One was resolving, and the other was non-resolving. Transiently gotten clinical signs of sepsis, developed antibodies to double-stranded DNA by about 3 weeks, and by about 6 weeks developed multiple organ failure. A beautiful model, is it not, to study non-resolving inflammation. One of the key cells that traverses that entire phase is a macrophage. And so when we compared our macrophages from a resolving inflammation, they're expressing TIM4 on the left-hand side, secreting IL-10, TGF-beta, but those from the non-resolving macrophages are not. And here's a snippet of our data. Just look at TIM4 on the left-hand side. I've told you that it's important resolution, apoptotic macrophage eating up molecule. Naive cells on the left-hand side, that is the amount of TIM4 on the macrophages of a naive peritoneal cavity. And the green bits are the amount of TIM4, slightly higher, if you can believe it, on the macrophages from the resolution phase. But from the non-resolving model, the amount of TIM4 is substantially reduced, in line with what we've seen in old people. The chronic inflammatory signals from this septic tissue is beginning to dampen resolution pathways. And many others I can't show today, but this is just for illustration. And then MHC class 2, which is a predictor of survival in sepsis patients, is also significantly down. And things like arginase inflammatory signals are up. We did omics on these macrophages, non-resolving macrophages compared to resolving macrophages. We discovered about 600 genes that are upregulated on these macrophages, and very few of your classical pro-inflammatory pathways. Very little in IL-1, very little in IL-6, very little in TNF-alpha. All of the classic inflammatory pathways really are not up, which is peculiar for a model that develops into chronicity. But there was about 600 genes that are upregulated. We curated these genes and we asked within the cell what are the likely regulators and transcription factors that might control these genes, and we identified about 6 of them. And this is the bit I used to hate about academics years ago. They talk just like I am now, and then they don't reveal the names of them because we're trying to get patents on them. So I apologise for that, I understand it. So we call these Resolution Inhibitory Pathways. Everybody in this game needs an acronym, Richard. RIPs. So therefore we can develop iRIPs, inhibitors for RIPs, or even MRIPs, modulators of RIPs. So it gives us latitude. And we believe that we would hypothesize that these are very important for dampening the body's own internal resolution immune healing pathways. And just to convince you of that, I'm just reminding you of what I showed you with TIM4. On the left-hand side, it's down in the red, inflamed macrophages, and if we block some of our RIPs using siRNA, what do we see? TIM4 in the paragraph here, it's now back up to very high levels. We can rejuvenate, and we can actually do the very same with class 2 and arginase. So in other words, non-resolving macrophage phenotype may be reverted to a resolving state by blocking some of our RIPs. You got that? Very key. And if we take one of these RIPs, you're asking, are they present perhaps in people with chronic diseases? We take sepsis, which we think is a very interesting disease for us and very fitting. This is control people. This is the single-cell RNA-seq from sepsis patients. Macrophages up here at the top left-hand corner, T cells, DCs, B cells, resting cells. There's very little of our candidate RIP in resting cells. But if we look at survivors, they are enriched. People who had sepsis, who are sick but survived, they have elevated RIPs within them. And if you look at the 2 on the right-hand side, you could agree that in those people who had died, there is even more. Placing our RIP molecules in macrophages of individuals who develop very severe sepsis and die. And we found the same then from mononucleophagocytes in patients with juvenile lupus. So what I wanted to wrap up in the last minute is non-resolving macrophages show suppressed resolution pathways. Our RIPs are upregulated within these macrophages, and we think it aligns well with chronic inflammatory disease. And our core hypothesis is chronically inflamed tissues silence pro-resolution biology. And so we want to understand how this comes about, and we want to rejuvenate immune resolution pathways to drive chronic inflammation into remission, or if you wish, make these bad, angry macrophages into good ones. And we think there's pervasiveness across many diseases, but we're focusing on aging, sepsis, and lupus for now, but potentially Crohn's disease. We put in a SMART grant to Innovate UK, bit of science there. This is our business developing plan, and as a basic scientist, this is always what I wanted to know about was business development, and it's really a transition for somebody like me to understand the business side of science. It really is. I think every scientist who does basic science should do this because they really know then how to make stuff happen. So this is my team. Shipa Mohammed is a clinical rheumatologist, and what is clear we can do, what is really interesting is these diseases like lupus are a collection of endotypes of diseases, and we're beginning to work at using responsiveness to drugs, blood biomarkers, and other things, subtypes or endotypes of lupus, for example, that is not responsive to B-cell therapy, but we think in which the pathology of the disease is driven by dysregulated macrophages underpinned by dysregulated RIPs. So we think by targeting endotypes of diseases, we can have tractability in the space. Craig Sutherland is business partner. Kostas is helping out with the proteomics of our pathways to understand more about them. And Dave Selwood is drug development. And yeah, thank you very much.
Perfectly on time, 47 seconds left, so.
I thought it was 47 seconds over.
No. And that was absolute amazing tour de force, and I now live in hope. There are, I presume, multiple questions, but I'll take the first one over here. Short questions, please, and short answers so that we can...
Hello there, thank you very much for a lovely talk. Traditionally in medicine, we split the inflammatory arthritis and osteoarthritis into 2 separate camps. To what extent do you believe that osteoarthritic changes can be opt for, you know what I'm trying to ask, can we underpin the inflammatory components of what's happening in joints to also affect osteoarthritis?
Right, I'll give you a very quick answer. We have put our blisters on the skin of rheumatoid patients, and we did osteoarthritis patients as a comparison. We found the very same resolution alteration in both people. These are two etiologically distinct diseases that had the very same accelerated resolution pathway in their skin, and we think this will inform on multimorbidities. Skin is not joint, but skin is a distal disease to the primary. Skin is a distal organ to the primary index organ. So we think this has utility in understanding multimorbidities. But I really know the answer to your question, but would we have seen these two different diseases, skin challenge models, compared to healthy controls, to show this very, very odd accelerated resolution phenotype?
Time for one more.
Thank you. I'm a lupus patient, so I was diagnosed 20 years ago at age 40. And my question, I'm in remission, should I be taking lismapimod or should I be taking your iRIPs?
Well, we haven't, we're in the process. Oh, you want to take our iRIPs? You do not look over 40. How about that? And that was even 20 years ago. So look, P38 inhibitors, I mean, GSK developed them 25, 30 years ago. They didn't do anything in rheumatoid, they didn't do anything in COPD, and that just tells you that the etiology of these diseases is not P38 MAP kinase driven. I think there's great utility in vaccine efficacy with P38 inhibitors. In terms of our iRIPs, we've got a lot of work to do.
Thank you. So I'd love to thank you again for a fantastic talk and discussion.